Okay, welcome back to our channel. Okay, if this is the first time you've seen my video, please ensure you subscribe to our YouTube channel and follow for more videos like this. So in today's video, what we're going to be looking at is current electricity. Actually, current electricity is a topic that has been giving so many student issues. I hear of cases student comes to my team like, "Oh, please take this topic. I don't understand." Calm down. I'm here for you. But you see, this current electricity is subdivided into three parts. Current electricity 1, where we're talking about this and solve some question. Current electricity 2, where we're going deeper into it, and current electricity 3, where we're looking at all the equipment and things related to current electricity. So make sure you subscribe so that when I make a video on current electricity 2, you'll be notified. Okay, so let's quickly look at our objective or what we have here. Okay, now firstly I want to make you understand that physics is not difficult. It's only difficult when you don't meet or when you have not seen someone who can teach you better the way you should understand it. So but I know and I believe that by the grace of God, if you can stay to the end of this video, current electricity, the beginning part will not be issue for you again. Where you'll be seeing questions on resistance and resistance is serious, you don't even know what to do, or see the brain behind this thing is understanding the concept. See, the brain behind calculation in physics is understanding the concept. So I plead with you, don't just watch the beginning and just stay to the end. And if you are watching this video from TikTok, please you will not get the full clip. Go to YouTube, search for Tutor Glycol, and you are going to get the full video on YouTube. So let's go. These are the objectives for today's class: meaning of current electricity, meaning of potential difference, and how is it. Many people think potential difference and EMF are the same. Not really sharp, but we're going to see. We will also understand electric circuit. We understand resistance and factors that can affect resistance. We also look at resistance in series, resistance in parallel under this. We're going to look at, I wrote it twice, still electric circuit. We're going to talk about the Ohm's law, the almighty Ohm's law that gives students dread. We're going to look at that. We're also going to be talking about work done in electric circuit. We're going to be talking about the power in the electric circuit. We're going to be talking about buying and selling of electrical power supply. We'll talk about this. I'm also going to talk about the heating effect of current, and also probably look at the fuse. Because question come out on this aspect. These are where many examples are tested. Yes, many examples are tested here. Yeah. So let's get to it. What is current electricity? Alright, so let's start off. What is current electricity? So current electricity is simply the rate. Take note, emphasis on the word rate. So I'm going to be giving you some keywords here. The rate first, the rate at which charge flow, the rate of flow of electric charge, rate of flow of charge. Let me just put it down. Quantity as charge, right? So current electricity, or when you hear current, the word current, because electricity can either be static. I'm going to make a video on what static electricity is. So electricity can actually be static or dynamic, that is static or flowing. The aspect of current, the aspect of electricity that deals with static charges, because we deal with charge. Anytime we talk about current, we're dealing with charge, very, very important. We're dealing with charge. So the aspect of electricity that talks about charges at rest, just like the way we have motion at rest and motion, like that's why we have bodies moving and bodies in motion, bodies at rest. The same way we have charges in motion, charges at rest. When the charges are at rest, we call it electrostatic. Static means not moving. So when you hear electrostatic physics, we are talking about aspect of physics that deals with charges that are not in motion, that are at rest. This is why that's why you have the ebonite rod, the glass rod, charging by friction, charging by all of those other parts. That is where we have electrostatic. But when you hear current electricity, it means charges that are flowing. There was a time I was making a video on simple harmonic motion. Yeah, I don't know if you have not, go and check that video. I said something under that. I said motion refers to the change in the position of an object with time. There is no how we are going to describe motion without talking about time. Time is a very precious thing. So when we say, now another thing I want you to take note of is the word rate. Anytime we use the word rate, it means over time. That thing is measured or talked about with respect to time. Time is involved, and this is why when we say acceleration, we say acceleration is the rate of change of velocity, right? Rate of change of velocity. So when we say rate of change of velocity, all means the change of velocity with time. So this is why we say acceleration is equal to velocity over time. You say velocity is equal to displacement over time, change of displacement with time. So when the word rate is used in physics, it means over time. That thing is measured with respect to time. And you know that time is one of the things that time waits for no man. There was a time even when we were little, then go to school, they made a marching song for time. Time waits for no one. Time does not wait. Whether you are moving, whether you are static, you are measured with respect to time. So when we say current, the current is represented with I. The symbol I is what we use to represent current. So from this definition, yes, for most definition, you can get your formula for most things. So mathematically, current I is equal to charge Q over time. Are you seeing it now? So rate of flow of charge, because the charges are flowing, that's why we call it current. They are not at rest. So rate of flow of charge with time. So current I is equal to charge Q over time. This is from this definition we got the formula for current. And it is also from this place we got the formula for. How many of you remember that formula? Q equals IT. Q equals IT. Where did they get Q equals IT from? Look at over 1. If I cross multiply, I have Q is equal to IT. So it simply means quantity of charge is current I times time, or charge is equal to quantity of charge over time. You can use them anywhere. Please take note of that. Very, very important. So what is current? Current is the rate of flow of charge, because the charges are flowing. That's why we call it current. Very important. So having known that, take note of these two formulas. Very, very important. Now, come in physics, most things are actually measured, because if we are talking about current and we cannot see it, it means we should be able to measure it. So the instrument that is used for measuring current is called the ammeter. Don't forget this. So these are potential questions that can come at ammeter. Ammeter is an instrument that is used for measuring current, and this ammeter measures current. Okay, and current is measured in ampere. Oh, take note, ampere. The unit that is current is used to measure is called amp. Now, ampere is the commonest unit. What I mean by common units, I mean unit that most people know, most textbooks use. So here, a current of 3 ampere, a current of 5 ampere, but that does not mean that's the only unit for current. Remember, for the formula for current, we have Q is equal to IT. Is that not it? So if Q equals IT, definitely, if I is equal to Q over T, and Q is measured in coulomb, T is in second. So another unit for my current will be what? Coulomb per second. T. This is where jam most times and portion test if a student truly understands something. A question can come at which of the following units is the unit of current. They can put I. They can say I, ampere. I. They can put volts. I, like 3 here. They can put coulomb per second. You write it in full. IV. They will put, let's say, a unit that is similar. Let's say coulomb, just coulomb. Let's say something like this. They will tell you that option A, I only. Option B, I and I. Option C, I, like all of them, and option D, none of the above. Most of them will put I only because they are familiar with only ampere. They just ampere and they will go, they are wrong, because this coulomb per second is also a unit, but it's not that common, and because sometimes it's very long. Okay, and sometimes too, most students, we know ampere, we also know coulomb per second, but because of tension, the option will not put it coulomb per second. The option will just put it coulomb. They say the right is full like this, coulomb. They will put a dash like this, second. This does not mean coulomb per second, please. This means coulomb times second, and it's wrong. Current is not coulomb times second, it is rather coulomb over second. So they just put this first one like this, and most of them, because they know that another unit of this is because they just saw coulomb and second, they repeat it, and it's wrong. This is how I teach my students on my time. You should be able to differentiate when you read or when you study something. Don't just move. You should be able to differentiate them. So these are ways through which you can be tested. So having known that, another thing I want us to take note of again is that, you see, an instrument can be sensitive. I want to differentiate between sensitivity and what they call it, precision and accuracy. So most times this is also used in physics. Most times it is actually used in physics. Sensitivity, the difference between sensitivity, I've seen a question on that, sensitivity, accuracy, and precision. So let's differentiate these three things so that when they tell an instrument is sensitive, you will know what it means. If I tell you that you are sensitive, what do I mean by that? So let's take, for example, you are sleeping, but anytime somebody walks through, you wake up, or anytime anything shakes you, it means you are sensitive. So sensitivity is the ability of an instrument to detect changes. The ability of an instrument to be able to detect things is what we call sensitivity. So when you hear a question tell you that the sensitivity of an instrument, ability for it to detect changes, that's what we call sensitivity. So ammeter and galvanometer, if you have read in your text, you know that the galvanometer is more sensitive than the ammeter. Galvanometer is an instrument that can actually measure potential difference and also and current. So when you want to measure very small current, we use galvanometer. We don't use ammeter because galvanometer is very sensitive, and this is what we need. So if I place my ammeter, let's say I have my ammeter here. Sorry for that. So let's say I have my ammeter. This is my ammeter. Ammeter, let me put A, and this is my galvanometer. Let me put G. I connect a wire to the two of them. I passed a current of 0.5 ampere through my ammeter and a current of 0.5 ampere through my galvanometer. You know the way the ammeter and galvanometer, they have a spring that just like your clock is, they can read time. So when the current of 0.5 ampere passes through this ammeter, the spring did not deflect. But when it passes through the galvanometer, it deflected. You saw that both of them has 0.5 ampere passing through them, but only this one deflect. Only this one showed that a current has actually passed through. The galvanometer is actually sensitive. We say the galvanometer is sensitive than the ammeter. But if I pass 2 ampere through this, it's deflected. That's to show that the ammeter is not able to catch small current, only some amount of current. So galvanometer is more sensitive than the ammeter. That's what I mean by sensitivity. Ability of an instrument to detect small changes. That's what we call sensitivity. Now, what is accuracy? Accuracy of an instrument is the ability to measure value close to the true value. When an instrument is able to measure a value close to the true value, we say the instrument is accurate. Should I give you an example? Let's say a current of 5 ampere is passing through this ammeter. A current of 5 ampere is passing through it, but the ammeter deflected and showed that 4.95 ampere is what is passing through. 4.95 is very close to 5. Is that not it? We say the ammeter is accurate. When an instrument is able to measure a value close to the true value, we say the instrument is accurate. Then what is precision? Precision is not the same as accuracy. Okay. Precision is when an instrument is able to measure several values that are close. So let's take for example now an instrument. I use an instrument to measure I use this ammeter to measure a particular current. It gave me 3 ampere. I use it the second time, it gave me 2.9. I use it the second time, it gave me 3.1. You see, the values the instrument keeps measuring are close value. They are not different, they are close value. We say the instrument is precise. Now I will give a real life, realistic something for you. So you have a footballer. He shots the ball the first time, it hits the bar. Shot it the second time, it hits the bar. Shot it the third time, hits the bar. That player is precise but not accurate. But if he shoots it the fourth time, it entered the goalpost, the player is now said to be accurate. That's the difference between accuracy and precision. So accuracy and precision are not the same. Precision is when an instrument measures values that are close, almost the same, close to the true value, almost the same. That's accurate. Several values, use it several times, it keeps giving you the same, almost the same answer, almost the same, then it is precise. But if it gives you the exact value or value very, very close to it, then it is said to be accurate. That's what I mean by sensitivity, accuracy, and precision. So under the meaning of current, we have understand what current is, instruments we use to measure current, difference between the unit of current, and some sensitivity, accuracy, and precision. Now we're going to move on. We want to look at meaning of potential difference and how it is different from electromotive force. But before we talk about that, it is important I quickly explain what an electric circuit is. Yeah, it is important. So what is an electric circuit? An electric circuit is a path in which the current flows, as easy as that. If your water in your house is flowing through pipe, right? The water represents the current, the pipe represents the path through which it flows. So the pipe is known as the circuit of the water. So a circuit, an electric circuit, is the path through which current flows. So this is how an electric circuit is drawn most time. Now, an electric circuit must have a battery, because the battery is the source of the current. An electric circuit must have a battery, it must have a switch, it must have a load, it must have an ammeter that measures current, it must have a voltmeter that measures potential difference. I'm still going to talk about potential difference. It must have a voltmeter, it has a resistor that gives resistance. We're going to know more about that under resistance. And Yeah, those simple things, and must have a load. A load is not a must, it has a load though, but a load is part of the thing that should be there. But the important things that must be there is the battery, the wire and the rest. Okay, so let me just draw that for you. So this is my battery. A battery has a longer terminal and a short terminal. The battery has the long terminal is called the positive terminal, that's the positive side. The short terminal is called the negative terminal. Current flows from the positive to the negative. Electron flows from the negative to the. Please take away. These are questions they can ask you in JAMB and WAEC and whatsoever. In what direction does current flow in a battery? From the positive terminal to the negative terminal. So for current, positive to negative. For electrons, negative to positive. Very, very important. But an easy way for you to remember this is this. This is the positive terminal, and this is the negative terminal. Positive charges move from this side, from this positive side. Positive charge move from the positive. This place, because this is positive, it will produce positive charge. Because this is negative, it produces negative charge. That's not it. So the current flows in the direction of the positive charge. So current will flow from here like this to this side, while electron will flow from here like this to this side. So in that way, you just need to ask you what direction. The longer one is the positive one, while the shorter one is the negative one. So I want to draw our electric circuit. Okay, very good. Let's look at our electric circuit. So the battery comes this way. This is our key. Okay, let me put this place here. Is our ammeter. Let's put the resistor here. This is our voltmeter. Okay, let's put the load like a bulb. Ammeter that measures current. Voltmeter, this is a resistor. This is a load. Load means that thing that the current want to power. If you're on your generator, why are you on your generator? To give light into your house, right? The light is the load. To on your fan, the fan is a load. Your TV is a load. So anything that is attached to the circuit so that current will be produced to it is all called the load. Don't forget that. So this is the key. Key is what actually completes the circuit. Key is like a bridge. It's like a bridge. So if the key is open, the magic current is produced now. I want to explain something. So take note. It is from this place now I'm going to differentiate between potential difference and EMF. Take note. Please follow me at this point. So this is the battery. Let me put B so you know. Battery. So the current is produced here. So if current is produced here, the current begins to move. But you see that the key is open. At this point, the key is open because there's a bridge. Sorry, the bridge is open. So the key is open. Let me write K here. So, can the current proceed? No. So if current is not proceeding, will ammeter measure anything? No. Will voltmeter detect anything? No. Will the light, the bulb that we attach, will it on? No. So when the key is open, this kind of circuit, remember a circuit is the path flow of current, the path that the current will pass, the pathway, that's just it. So if key is open, the circuit is known as what? Open circuit. The circuit is known as open circuit. But if the key is closed, like this, so it will continue. The circuit is known as what? Closed circuit. Very, very important to take note of that. So when key is closed, it's known as closed circuit. When key is open, it's known as open circuit. When there is no load, attached, the circuit is called a short circuit. So we have three kinds of circuits. What are they? Open circuit, closed circuit, and short circuit. So how do we differentiate them? Open circuit when key is open, closed circuit when key is closed, short circuit when there is no load. I hope you are following me. So this is how we differentiate the three kinds of circuit. Now moving on, we already understand what the circuit is. A circuit, my diagram might not be 100% correct, but this is just the main thing concerning the circuit, okay? And that you have to understand again is that your ammeter should be connected to your battery in series. Please, series means anytime we say something is in series, because we are going to be looking at that very well under resistance. Anytime we say something is in series, it means that the thing is connected in such a way that the one thing is passing through and touch the other. So if I hold an electric pole and you hold me, if the thing shock me, will it not shock you? Exactly. we are in series. When something passes through one and enter through the other, we say it's series. So if the current comes this way like this now, it will the same amount of current that is coming through the battery. If it is 10 ampere that is coming through the battery, it is the 10 ampere that will be registered by the ammeter, because it is in series with it. So in a circuit, your ampere must be connected in series to your battery, but your voltmeter must be connected in parallel to it. A parallel means that it's not as if it will not reach it, but it's not all of them. Now let's take it for example. What we usually use to know series and parallel is our current. If this current moves, the 10 ampere moves and reaches it, the whole of the 10 ampere will pass through this thing, so it is in series. But when it comes here, it is not all of the 10 ampere that will come to the voltage. Some of them will go this way, while some of them will go this way. It will be divided depending on the resistance. Okay, we are going to understand that under resistance soon. Depending on the resistance, it will determine. So this voltage, because it's not all of the current that is coming to it, it is said to be in parallel. So when the connection is not direct, it is parallel. When the connection is direct, it is series in a layman term. Okay, are you getting me now? So your voltmeter should be parallel to your battery. Your ammeter should be in series with your battery in a circuit connection. So we have understood that now. Now let's look at meaning of potential difference and EMF. Before I talk about what is potential difference, potential difference is actually the energy needed to move a positive charge or to move one coulomb of charge from one point to another point in the circuit. The energy, take note, the energy needed to move a positive charge or to move one coulomb of charge from one point to another point. That's what we call potential difference. Or it is the difference in potential. It is the difference in potential energy between the two terminals of the battery. The potential difference in potential. That's what potential difference. So the difference between the potential of one point and another point that you are looking at is what we call the potential difference. Are you with me now? Please let's follow me. Now, what about EMF? EMF is actually the energy needed to take one coulomb of charge, or to take the one coulomb of charge or a positive charge around the circuit. The energy needed to take one coulomb of charge around the circuit. Now, that can look confusing to you as a student, but I'm going to be using a realistic distance for you to understand. But before we proceed, the battery is what produces the potential difference or the EMF. We'll see how the EMF is different. Let's say this battery has an EMF, that is the energy needed to power a charge around this whole circuit without giving out to the load is what we call potential difference. So if I on my generator is my source of current, right? If I on my generator without connecting, okay, should I even use let me use this NEPA meter, that meter we have in our house. I hope you know that when your meter is connected, the appliances you use will be draining energy from the meter. Is that not it? So if you on your light, that's how you see some father will say, off that light if you are not using that light, off the TV, you just on TV down like that. You don't know the meter will be draining and blah blah blah. Good. So let's say when your father made payment for the meter, let's say your meter has 100 joule of energy. Before you started using it, this 100 joule of energy is the energy that can power whatever you have in your house. Is that not it? And each of the appliances you have in your house cannot drain the whole of the 100 joule once. If you on TV, let's say like 2 joule will go to TV. If you on fan, let's say like 5 joule will go to fan. If you on fridge, let's say like 20 joule will go to fridge. You can see there is divided. This 100 joule is the actual amount of energy that is needed to power the whole house. This 100 joules are called the EMF, the amount of energy needed to take the coulomb, to take the current around the circuit is what we call the EMF. The 2 joules given to light, 10 joules given to TV, those ones are what we call potential difference. Why? If the light is somewhere here, right? This is where the energy source is coming from, right? So this is point A, this is point B. So the energy needed to take the current from this point A to this point B, difference. The energy, there must be an energy difference. Remember, we say in diffusion in biology that we say molecules will move from a region of higher concentration to a region of lower concentration until it is evenly distributed. Once it is evenly distributed, there will not be movement again. So if these two sides does not have a difference in potential. The potential here is low, the potential here is high. This is why it needs current. Are you with me? So energy will flow from here to here. Potential difference if there is a bulb here. Are you with me? Sorry. If there is a bulb here, so there must be an energy difference between this side and this side for it to flow. So potential difference actually refers to the difference in potential between one point and another point. Why the EMF is the energy that is actually, that's where we get our potential from. As I have described here. Do you get what I'm saying now? Exactly. So when we talk about potential, so most times students think potential difference and EMF, and they are not the same thing. The EMF is actually the energy the battery has to produce, the actual amount of energy. Once the EMF finishes, you don't finish, there's nothing. So it is from this EMF we get difference potential. Oh, potential difference here, potential difference here. So potential difference is actually between 2 points. So the energy needed to take one coulomb of charge from the battery to a particular point in the circuit, maybe to the bulb, maybe to the fan, maybe to the TV. The energy needed to take it from this place to that place, so called the potential difference. But if we are supplying bulb, fan, TV, and whatsoever, the energy needed to take the current around the whole circuit when it's not powering anything. It's all called potential. It's all called EMF. Are you with me now? When it is not powering, because if it begins to now, imagine when your dad came. He came with 100 joule. That's what your daddy read. But he now left, he was not in the house. And your junior brother came. He on the TV. You know some of the energy will be drained out because it has power something. He on this and on that. Then after he finished, he left. You, the previous day that you saw that, oh, the meter has gone off. Daddy said we'll fill it the next day. So you went out before. When you came back, you saw that the meter has been charged. You now look at it, oh. And what you were seeing 80 joule. But you already filled 100 joule. So when you came, you now saw 80. Is it 80 joule, madam? Okay, maybe it does not. It's 80 joule. You know, to you now, you thought the 80 joule is actually the real EMF, but that's not the EMF. That's how we said the EMF of a battery is actually the amount of energy that is needed to power the whole circuit when no load is connected. Because when your brother connected some load, somewhere left. So immediately you connect load, what is registering at that point now is not the EMF, it is the potential difference. Because the moment if the circuit is open now, let's say the circuit is open. I'm taking it to somewhere. Let's say the circuit is open this way. If the circuit is open now, the EMF now, whatever EMF, whatever voltage this your circuit is registering is actually the EMF. Whatever voltage, because the circuit is closed, because the circuit is open. So as long as the circuit is open, this particular battery cannot power any load because there is no way it can be connected to it. So the energy of this circuit when the circuit is actually open is what we call the EMF. And this is why your textbook will tell you that another way you can define EMF, it is the amount of energy needed to power one coulomb of electric charge when the circuit is open. They will not tell you when the circuit is closed. This is another question. So when the circuit is open, the energy is called the EMF. But when it is closed, it is the potential difference because load has been attracted to it. Are you following? So it is the load now that brings about potential difference. I hope I've been able to differentiate both this and this. Are you? So let's move on. So after we have known that now, we would like to look at let's see resistance. Resistance and the factor that affect resistance. What is resistance? Now, just in an English or in a layman, resistance is opposition. When you are trying to move, something is resisting you. That's what we call resistance. So in current electricity, when we say resistance, what is moving is the current. So resistance is the opposition to the flow of current. The force restricting current from moving is what we call resistance. So opposition to the flow of current is what we call resistance. The instrument that measures the resistance is called the resistor. The instrument that measures the potential is called the voltmeter. We have other instruments though that I said the galvanometer can measure potential. We have the potentiometer. Other instruments can measure voltage. But resistor is actually opposition to the flow of current. What is used to measure resistance is the resistor. Resistor is the instrument. Resistance is the process. Get it? Resistance is the process. Resistor is the instrument. Unit of voltmeter. Unit of potential difference is volt. Take the voltage. That's volt. Volt. Don't forget. Volt is the unit of potential difference. Unit of resistance is ohms. Don't forget. Or it can be written as this. ohms. Okay, very very important. Take note the unit, ohms, voltmeter. Okay, so resistance now has some factors that now anytime we refer to factor in physics or anytime we talk about factor in physics, factor actually talk about anything that has an effect. It can be positively, it can be negative. As long as that thing has an effect on a particular thing, it is a factor. So factors affecting resistance, we have the length. The longer the length of the conductor, the higher the resistance. So resistance is directly proportional to the length. So the longer the length, the higher. We have area too. So the area is that resistance, and one way through which I usually use to remember this thing is this particular formula. Now I'm going to talk about under resistivity, not under this video. So you see this formula now. That's the formula which I used to remember their relationship. So if I make resistance over the formula, I'll have resistance is equal to times L over A. So this way I used to remember which one is inversely proportional. This is resistance, this is resistivity, this is length, this is area. So since resistance and length they are directly proportional, it means increase in length, it means increase in resistance. So the longer the length of the conductor, it means the higher the resistance. Resistance and area are inversely proportional, which means the higher the area or the increase in area means the decrease in resistance. So a higher area or if the area is increased, the resistance will reduce. If the length is increased, the resistance will reduce. That's one way I used to remember resistance is factor that affects resistance. Another factor that is affecting resistance is what we call it is temperature. Okay, let's take it. I want to explain something under that. Temperature. Temperature is a factor that is affecting resistance. So please take note that for metallic conductors, and what is a conductor first? A conductor is anything that can conduct, right? That allows the passage of current through. That's what a conductor is. So we have metallic conductor, we have non-metallic conductor, e.g. graphite. Graphite is a non-metallic conductor. It conducts electric current, but it's a non-metal. Non-metallic means it is a non-metal, but then it's conducting. So graphite, that's carbon, an allotrope of carbon. Then we have metallic conductor. For metallic conductor, if you increase the temperature, resistance will also increase. I'm literally teaching you what to have in your textbook. If you can watch this video to the end, I'm telling you, you don't need to read your textbook again, because most of this thing I'm saying, some textbook will not even tell you or explain it better. So just make sure you watch this video. So metallic conductor, an increase in temperature means increase in what? Increase in resistance. For non-metallic conductor, an increase in temperature means decrease resistance. That is, for non-metallic conductor, the relationship between temperature and resistance are inverse. See, when you see any relationship that is inverse, it means when one is increasing, the other will decrease. But when it is direct, when one is increasing, the other will decrease. So for metallic conductor, that is metal, you know your metal, and sodium, zinc, and all the metal. So metallic conductor, increase in temperature increases resistance. For non-metallic, increase in temperature decreases resistance. There are other substances that whether you increase temperature or you don't increase it, there is no change in resistance. Example of substance like that is constantan and manganese. Constantan and manganese. These two materials is in your textbook. Let me know, you can see it in your question. These two materials, temperature has no effect on that resistance. So because whether an increase in temperature or decrease, it does not affect that resistance, they use them to make rheostat. Rheostat means a resistor that this resistance does not change, a fixed resistance. Unlike other resistors unlike other resistance of some material that changes with temperature, these two substances, because temperature does not affect their resistance, they use them as a rheostat. A rheostat is a resistor. A rheostat, I feel the marker, I don't know why it's not. A rheostat is a resistor that its resistance does not change, it is not affected, it's a constant resistance. So that is that. So that's about the factors affecting resistance. So we want to look at now resistance in series and resistance in parallel. Now, resistance is series. What do we mean? I've already explained what series means. When they are joined end to end. So when a resistor is joined end to end, we say the resistor are in series. So for example, I have R1, R2, R3. They are joined end to end. These resistors are said to be in series. And when a resistor are joined in series, their total resistance, R total, RT, the total resistance is simply gotten by adding them together. R1 plus R2 plus R3. This is how you get that total resistance. Another key important thing you have to understand is that the current flowing through each of them is the same. So let's say a question says current of 5 ampere passes through R1, 5 ampere. What is the current flowing through R3? You don't need to solve. It's the same thing because they are in series. This is a key point. See, understand the concept, you will not have issue. It's a key point. Since current of R1 passes through this one, 5 ampere, it means the current passing through this one will also be 5 ampere. So imagine this is a person. If this person is shocked and all of them are connected, this third person will be shocked. This is why we say they are in series. So when resistors are in series, the current flowing through each of them are the same. Very important, please. And the total resistance is got by adding each of them together. Concerning voltage, when they are in series, the voltage passing through them is not the same. The voltage of this one is different from the voltage of this one. It's different from the voltage of this one. So this is V1, this is V2, this is V3. So if you want to get that total voltage VT is simply V1 plus V2 plus V3. The total voltage is not the same, so you can find the total voltage. So let's say when I get to Ohm's law, I'm going to explain Ohm's law. But for those of you who already know what Ohm's law is, Ohm's law is what V equals IR. I'll explain it, but I just want to use something to explain something. So if from Ohm's law we know V equals IR, and the question asks me that, okay, if a current of 5 ampere passes through this circuit, right, and the resistor R1 is 3 ohm, what is the voltage in R1? Simple. I'll say V1 from the Ohm's law. V1 is equal to I times R1. Are you seeing the differences now? I want to make you understand. This is the old circuit. From here, this point A here is the beginning of the circuit. This point B here is the end of the circuit. So from this circuit AB now, the total circuit here now, they want me to find, the question want me to find the voltage of this one, of this R1. And the resistor here is 3 ohm. So I will simply use Ohm's law. V1 is equal to I times R1. Why did I not put I1? The reason I don't put I1 is because the current flowing through all of them is the same. So I just use I. So the current flowing through all of them is the same, and it's also the current flowing through the circuit. Are you with me? So the current flowing through the circuit is the same as the current flowing through this, and this. I hope I'm getting it. Because sometimes the question can just tell you that the current flowing through R2 is 5 ampere. What is the current in the circuit? The student will take a pen and pad. That's why I say understand the matters. Understand first, is it in series or is it in parallel? Once it is in series, if the question now look, let's say they draw a question like this for you, and they say, okay, the current that flows through the resistor R2 is 5 ampere. What is the current in the circuit? Somebody will now pick a biro and begin to solve. Why are you solving? Because they are in series, the same current pass through the circuit, the same current pass each of the resistors. You don't need to solve. Just go ahead and pick it. What the examiner is trying to do is trying to test you if you actually understood what this thing is saying. He's not trying to make you so. He's trying to. You know, there are some examiner that will come to you and be like, this person, no, let me test and see if you actually understood what I'm saying. Are you following that? So that is that about that. So R2. So if I want to get the voltage of this one, I'll simply use Ohm's law. So what is I? 5. What is R1? 3. 5 times 3. That's 50. Are you with me? 5 times 3, that's 50. If I now go ahead and say, okay, since they want me to find the voltage in R1, this is what some students are so funny because they don't understand. This is why I will always encourage you that you try and join our online classes. So I will be bringing things like this to you. Some students are so funny, they'll say, okay, since they say I should find the voltage in the resistor 1, I will look over the total resistance, R1 plus R2. To find the total, when they get the total resistance, and they'll not use the total resistance as their R1. You are wrong. They only ask you for R1, not for the whole circuit. But if the question says, find the voltage of the whole circuit, then I will not use R1. I will have to use my total resistance. That's how this stuff is. So for resistance in series, the current flowing through them is the same. The voltage flowing through them is not the same. Each of them have different resistor, different voltage. But if you add their voltage together, it will give you the voltage of the circuit. Are you following me now? So that's it. Do you get what I'm saying now? So the voltage flow passing through each of them are not are not the same, but if you add it together, it will give you total voltage. So that is for resistance in series. Now let's look at resistance in parallel. For resistors in parallel, rather, not resistance, resistor in parallel. So for resistor in parallel, they are not joined end to end, rather these are resistor in parallel. Is like this. This point A, this point B. So we have R1, R2, R3. Are you seeing this now? So this is what we call resistor in parallel. When the resistor are arranged in parallel, they are not. You see, they are not joined end to end. Okay, you can see that they are different. You can see this one. The only way all of them are connected is at the two ends. So if a current is coming in this direction, current A, what do you think? Is it the same current that will flow through all of them? No. The moment current A reaches there, it will divide. Are you following now? It will divide. So the amount of current that flows through each of the resistors depends on that resistance. And hope you remember we said resistance is the opposition to the flow of current. So if this resistance is 5 and this one is 3 and this one is 2, which of them do you think will carry the highest amount of current? Good, 2. Now I've seen a question like this. It's not calculation, it's theoretical. They say which of them has the highest current. Physics is not hard. This is it here. And understand, we say resistance is the opposition. So which means the part that has the highest opposition, small current will flow. Imagine in one road, you have 10 people trying to block you from passing. In another road, you have 5 people trying to block you from passing. In the third road, you have only one person trying to block you from passing. Which of these roads do you think will have the highest chances of passing? The one with one road. So the resistor with the part where the current has the highest chance of passing is the one with 2 ohms. Because here it has a low resistance. So a part that has a low resistance will have higher current. And this is why you see that most circuits, they are designed to have a low resistance, except in some cases where they want low current to flow. If a circuit that want to power a load, if the resistance is high, the current that will flow through that circuit will be small. It will be small. Are you following now? So you see, you can see now, it's a question, take notes please. So the current that will fly, so how do you now know which part will have the highest current? Is this one. This part with the lowest current will be this one. As easy as that. So when the current passes it, it's not converging and flow through. Now you will now understand. From this now, you will now understand that for resistance in parallel, it is not the same current that flows through them. The current differ. Unlike resistance in series. For those in parallel, the current differ. This one carries a separate current, the lowest current, the highest current, and the medium current. But at the other end, all the current converge and continue. Are you with me now? So current is not the same in all of them. But in this case, the voltage is the same. Remember when I was talking about circuits, what did I say? I said that for a circuit, are you listening? For a circuit, the voltmeter is connected in parallel to the circuit. So if the resistors are in parallel, it means the voltmeter, it means that it is in the same direction with the voltage. So the voltage of R1, R2, R3 is the same. Don't be confused. The voltage of the circuit, if we say the voltage of the circuit is 5 volts, it also means that the voltage in R1 is 5, the voltage in R2 is 5, the voltage in R3 is 5. All of them has 5, 5, 5. So when they ask you what is the voltage of R2, you don't need to start solving, just write 5 there. All of them has the same voltage because the resistors are in parallel, and so it is in the same direction with the voltmeter of the circuit. Do you remember that of series? In series, you said the voltmeter are not the same, right? Because in series connection, it is not in the same direction with voltmeter, but rather it is in the same direction with ampere. It's not difficult. Hope you get the differences. Are you following now? Exactly. So let's take note. Very, very important. Then, if you want to get the total resistance RT is gotten by saying adding the inverse of each of them. 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so using the same procedure I used for a resistor. If they ask me that what is the current flowing through this thing, since I already know that the voltage is the same from Ohm's law, since I already know, I was okay. Since voltage is 5, the current and this resistor here, let's say is 2 ohm. R2 is 2. Then I can use Ohm's law to get my current. We just say I is equal to V over R. So V is 5, R is 2. 5 over 2 is 2.5. Like current that will flow into this is 2.5. Now sometimes they will give you the current flowing through a particular resistor in a particular one, and they want you to find the current in the whole of the circuit. For you to get that, you have to know the current here, the current here, then add it all together. Are you know? Or you can simply say there are different ways you can do it, but what I'm playing at, or what I'm driving at is I'm trying to pass the understanding to you that you have to understand it first before you be able to solve something. The stuff is not difficult. That's the difference between resistor in parallel and resistor in series. We are going to check on some examples later on. So I've talked about this. So let's talk about the Ohm's law. What is Ohm's law? It's a law. So if it's a law, we can bring it into mathematical computation. Ohm's law states that the current flowing through a metallic conductor, let's say a wire, is directly proportional to the potential difference across the ends of the conductor. If temperature and every other factors like length, area are kept constant. Remember, we say that resistance have factors that are affecting. So if we keep all of these factors, the temperature, the length, the area, whatsoever factor, if we keep it constant, keeping it constant means if we do not allow those factors interfere with what we are saying, then the voltage is directly proportional to the current. But if these factors are not kept constant, it will not be directly proportional. Something will happen. There will be a change. Just like in physics, when I solve some questions in project, they say, let air resistance be kept constant. They say, take air resistance, or let air resistance be negligible. Negligible means it is constant. We are not considering it. Are you with me? So if every other factor is kept constant, if temperature is kept constant, if we do not consider the effect temperature will cause, if we do not consider the effect length will cause, if we do not consider the effect area will cause, as long as all of these physical factors are kept constant, then by Ohm's law, the potential difference across the end of the conductor is directly proportional to the current, flowing through the circuit. Are you with me? Or flowing through the conductor. So see, this is the conductor. This is point A. This is point B. The current flowing through this thing is directly proportional to the potential difference across its end. So for mathematics, we know we always have a constant. We put equal sign. So we have something like this. V is equal to I. This arrow is the constant of proportionality that came. Remember in mathematics, if we have proportionality sign, then a constant K will always come out. So this arrow is the proportionality constant that came from this whole process. That's how we get this Ohm's law. So if I have my resistance, if I have my current, I can get my potential difference for the voltage. That's simply what Ohm's law is. Any conductor that obeys Ohm's law are called ohmic conductor. Jam question, take note. Ohmic conductor. Why the one that does not obey it is called non-ohmic conductor. Example of non-ohmic conductor are those diode, rectifier, transistor, all those ones that are non-ohmic conductor. So the graph, since they are directly proportional, the graph of Ohm's law, this is how it looks like. These are potential question, Cosine and Jam. Take note. So the graph is like this. This is V. This is I. So since they are directly proportional, it means that as one is increasing, the other one will increase. So this is how it looks like. These are the graph looks like. So a ohmic conductor, it's by Ohm's law, this is how the graph will look like. But a non-ohmic conductor will not look like this. Probably it will be something like this. Something like this. It's not look like that because it does not obey Ohm's law. So by Ohm's law, as voltage is increasing, current is also increasing. That's what Ohm's law is trying to say. So I've understood Ohm's law, and let's look at work done in an electric circuit. Work done in an electric circuit. Okay. So we know the voltage. The voltage V is giving us work over charge. So work done will be, this is work, this is charge, this is voltage. Work done will be Q times V. So definitely you know that work is actually in physics force times distance. We say work is done when the force is applied and moves another through distance. So definitely work, this is our charge, this is our potential difference between the two ends, right? So work done is actually the energy that is needed to move this charge through 2 points. Okay, now just what's work done. So anytime they ask you what is the work done in an electric circuit, just know is the charge times the voltage, okay, or the potential difference. Now I hope you also remember that. Q is equal to IT. I taught you that earlier. I times T. So Q is equal to IT. Knowing that Q is equal to IT, so this whole place is obtained by this IT. Then bring my V down times V. Every time I have I V T. This is the formula you are seeing in your book most of your textbook, and you have to add the V, add the I, this I, from Q equals IT. So if I multiply it together in IVT, so work done can be Q times V, work done can also be IVT. Now we already understood Ohm's law, from Ohm's law, say V is what? I times R. So anytime I see V, I can put that I times R. So my work done can also be from this IVT, only V alone is IR. So this is my first I, this is it here. And my V now is I times R from Ohm's law, right? That's I times R. This is my T, this is it here. Opening the bracket, I will have I times I is I squared times R times T. That's how you get the formula of I squared RT. That's how they get the formula. You see that physics is not something you should cram. Understanding it will just help you. So I don't encourage my students to cram. I just let them understand the concept and you're good to go. So this is the work done. The work done can either be IVT. You see, this formula, it depends on your parameter. What is parameter? Parameter are those set of value given to you in the equation that can help you solve the question. So once you know your parameter, if they give you current, voltage, and time, you know this is the formula you're using. If they give you current, resistance, and time, you know this is the formula you're using. If they give you charge and potential, you know this is the formula. So the formula you will use to solve it depends on the parameter given. But these three formulas are the formula you can use to find work. So I've done this. Let's look at power in the second. Power, see, if you can know work, you can say why you see why you don't need to cram. In my early days in secondary school, then when I was dealing with this thing, I find it so difficult to solve for some point. If I will have to cram the formula for work done separately, cram the formula for power separately, you can see how much work we are giving ourselves. Very easy. What is power? Power is work done over time. Can you ask man? Power is work done over time. So if power is work done over time, all I simply need to do, my formula for work done, divide it by time, I will get my power. Very, very easy. Look at it. So my first power will be what? Since power is what? Work done over time. So first work done is Q times V. So my formula for power will be Q times V over time. My second work done is IVT, right? My other formula for power will be IVT over time. Since there's time here, they will cancel out. My power will be what? IV. I also have another formula, I square RT. So my power will also be P is equal to I square RT over time. Time will cancel time. We'll have power equals I square R. You need to cram this in. So once you know this one, just divide it by time. You are good to go. So that's it. If you can even know the formula for work done of electric circuit, if you know it, all you have to do is that anywhere you have your work done, divide it by time, you get your power. What is hard here is not difficult. You can see that current electricity is not how many minutes we have been able to understand work done and power. It's not difficult. So the next one we're going to be looking at is buying and selling of electrical power. Now you see, I made an example or an illustration using your meter that time, right? Now, this concept actually is used by those of us that use NEPA light. Almost everybody uses NEPA light. Before you change your NEPA light to meter, there's something you pay every month, right? You collect direct cost. If you use direct cost, but the best way to actually understand this is using the meter process, where it works for both. You know, every month NEPA people come, this is your NEPA bill, they'll give you NEPA bill, this amount of this in your house. And you know, because the NEPA bill is they want to cut somebody's neck off by NEPA, so that they can claim that your NEPA bill for this month is 50,000. And you ask yourself, what do I have inside my house? I do not have fridge. Sometimes they bring the light, before they bring the light, it will take years. How come? So this is the reason why many people switch to meter. Not because of anything. The reason is because NEPA most time we keep adding amount of Nigeria. Keep adding so much money. Maybe you are staying in a place in a 2-bedroom flat where they are like it's a duplex, but it's 2-bedroom flat, and they use direct current. Maybe your own 2-bedroom flat, the only thing you have is a TV, but your neighbor has let's say has fridge, TV, washing machine, have everything. But anytime they bring NEPA bill at the end of the month, your neighbor will be sharing the money the same. Maybe NEPA bill at the end of the month is 100,000. The neighbor will not pay 50,000. Are you like what that? Then you now, because of this, you now say, I want to use meter. At least the meter will be showing me the reading of what I'm using at the end of. I'll be seeing it there. This is why many people go for meter. So when you get your meter, the way the meter has different value there that shows you how you are using your electricity in your house. Okay, you want TV, it will read. You want this, it will read. and so on and so forth. So this is actually how this concept actually comes. This concept here, you can say physics is actually used in real life. If you understand physics, you can bring it. Physics is real life. It's real life. So if you understand physics, it is real life. So knowing this thing will not help you understand how these NEPA things are connected or are calculated. So when you are buying or selling any electrical power, it's usually calculated in kilowatts. The energy you use is calculated in kilowatts. Now, watts is a unit of power. I didn't even say it there. Watt is a unit of power. We also have other unit of power as horsepower. We have joule per second. Since joule is unit of energy and power is work done over time, say joule per second. So watt is the commonest unit of power. Kilo is just like when you have 1,000 watts. So 1,000 watts equals 1 kilowatt. So when you have watt and the question wants you to change to kilowatt, just divide it by 1,000. So kilowatt means 1,000 watts per hour. So this means this kilowatt is the energy you are using. This is how they calculate the energy used by your current or whatsoever. So kilowatt. So if you are using 1 kilowatt hour, 2 kilowatt, that's how it is. So kilowatt is the power we use in 1 hour. So what this means is 1 kilowatt hour, 1 power in 1 hour. Are you following me now? So that's how this thing is calculated. Now let me quickly go to what we are trying to say here. So haven't understood this now. Kilowatt hour, we already understand that now. Every of your appliance in your house, they have a particular amount of energy they take. They have a particular amount of power they take. The power they use, they have a particular. One can be using at 2 kilowatt hour, one can be using at 3. So whatever you use in your home, if those NEPA people come, or if your meter want to calculate, they calculate it based on what you are using. And yes, I remember some time when I was still small, a particular NEPA man entered the compound and say, I was like, they were arguing about the thing, and the man said, oh yeah, open your door, let me see your door. The man began to look at, oh, you have fridge, you have this, you have that. Then I was wondering, what does fridge and all of this have to do with NEPA bill? It was now I now understood. Each of these equipment or appliance you have, each of them suck a particular amount of energy. Remember when I was explaining EMF and the rest, they are taking a particular amount of energy from all of these sources. Exactly. So they are calculated based on this. So if you have a light bulb, I hope you know if you want to go and buy bulb. What do you say? I want to buy 50 watts bulb. I want to buy 100 watts bulb, because they are calculated in the amount of energy they take. So if you have a 50 watt bulb now, 50 watt, a bulb that is 50 watts. This bulb now, and this 50 watt bulb, you use it for 3 hours. If they want to calculate the energy you have used, they will say, okay, since it's 50 watt bulb, remember it is measured in what? It is measured in kilowatt, not in watt. They will change this 50 watt to kilowatt by dividing by 1,000. I think that will give you 0.05. So it means your bulb in kilowatt is what? 0.05 kilowatts, right? Now that they've gotten the power, or the power your bulb is using. They do not must. Oh, how many hours did you use it? 3 hours. 0.05 kilowatt times 3. So this will give you 3 times 5, 15, 5, 1, 3 times 8, that's 1. Now this will give you 0.15 kilowatt hour. It means the amount of energy you have used is 0.15 kilowatt hour. So if the question says, okay, by the NEPA bill, they say, okay, 1 kilowatt hour is 20 naira. So if you are using 0.15, if you have used 0.15 kilowatt hour, it means you multiply 20 naira by 0.15 kilowatt hour. That will be, where's my calculator? So 0.15 times 20. So that's how it's 3, which means you are paying 3 naira. So that's how they give you a payment. So you are paying 3 naira, you are paying 20 naira, you are paying 10. This is how it is calculated. So how do we solve questions on buying an electrical? Is simply know the total power your appliances are using first. Secondly, how many hours did you use it? 2. It must be in hour, and the power must be in kilowatt. How many hours did you use it? 2. Thirdly, find the energy. Energy is power times time. So multiply the power by time. Then use the amounts given to you in the question to find it, as easy as that. We are going to solve examples soon anyways. And lastly, I want to talk about the heating effect of the coil. Now, always know in your mind, or have this in the back of your mind, when a current flows through a particular conductor, it converts the electrical energy to heat energy. And this is why when the current is flowing through a particular conductor, if you hold it, it is hot. Are you with me? It is hot. It will be hot. It is because as the current is flowing, it converts electrical energy to heat energy. And that's the principle used in your electric pressing iron. When you plug your iron, have you never wondered when you plug iron to your socket and the iron becomes hot? Why is it not shocking? Instead of it to shock, it's because the current is being converted. There are coils inside of that convert the electrical energy from the socket to heat energy in your iron. So your iron becomes hot and you use it to press your clothes. That's the principle behind the heating effect of a coil. Are you with me? So sometimes person will ask you, oh, this particular appliance, what is the heating effect of this coil? The formula we use to find the heating effect, that's how I'm trying to go in here, because there's some person like that. The formula we use, if they ask you, what is the formula for finding the heating effect of a coil? The formula is H is equal to I square RT. And the good thing about this whole thing is that because this is a heat, and heat is a form of energy, and although I've not taught energy, I'm going to take time to teach that. From what we know on energy is not created or destroyed, but can be converted from one form to another form. So we can say electrical energy converted to heat energy. Is that not it? So electrical energy I square RT is what is converted to this heat energy that you are using your pressing iron. Under heat, there's a formula we have, the MC change the theta, right? MC change the theta. So I can equate this to I square RT. So from here, they can ask me a question and say, okay, what is the temperature? What is the temperature of my iron? If the mass of my iron is this and the specific capacity of my iron is this, if so amount of current flows through it, through a resist and blah blah, give you a question, all you have to do is, this is not difficult. So students will say a question that, oh, they don't teach me this one. It's easy. It is from the heating effect of a coil. So what we know is that when current passes through a conductor, the electrical energy is converted to heat energy. So you can simply use heat energy. Since electrical energy is converted to heat energy, I can equate. I made a video recently, a short video on how mechanical energy, kinetic energy is converted to potential energy. You should check on YouTube and TikTok to see. So this is just basically how this works, the heating effect of a coil. So the formula for finding the heating effect of a coil is I square RT. Now, lastly, I want to talk about a fuse. A fuse is actually a device that has a low melting point. What this fuse is actually important. It is used to break a circuit. A fuse is a device that has a low melting point that is used to break a circuit. Or a fuse is a safety device. Take note. You can ask which of the following is a safety device with low melting point and is used to break a circuit. What the fuse use? Many of you may hear your father buy. Those of you that are in secondary, when I say I want to buy a fuse, or go and buy a fuse. What it actually does is a safety device. This is it here. When current flows through a circuit, and remember I said when current is flowing, it's what it gives out, it converts electrical energy to heat energy. So the heat energy, when something has higher heat, it is hot. So when a higher current is coming, because the higher the current, the higher the heat. The higher the current, the higher the heat energy. So when a high current is coming, let's say, okay, in your TV, the amount of current that can power your TV is, let's say, 3 ampere. Anything more than 3 ampere can make your. This is why you see many times your TV blow. You just never will just break on, and the current will be so high. Yes, your TV will just blow. The TV don't blow. My charger don't blow. A fuse can help you regulate this. This is what a fuse do. When you attach a fuse to your circuit, when a current that has a high value is coming, and once the current comes, the current will reach the fuse first before it reaches your appliance. So because the fuse is made with a low melting point, as the current, the fuse, this one is a high, the fuse will burn, and it's immediately the fuse burn, the fuse will cut the wire. Current will not be able to transmit to where your appliance, and your appliance will not get burnt. If you know that this is what stabilizer actually do. Your stabilizer is for your fridge. Many people, when they want to buy fridge, they'll just use stabilizer. The stabilizer, what the stabilizer does is, the difference between the stabilizer and the fuse is that the stabilizer will not cut the DC. What the stabilizer will do? Stabilizer will take the whole current into itself, regulate it, and give the acquired amount required by your appliance. But a fuse does not have that power to take it. Rather, a fuse will blow. The fuse itself will sacrifice itself. It will cut off from the current. So it will divide. The fuse will act like the key in the circuit. It will break the circuit. Are you with me? It will break the circuit, stopping the high current from reaching your device. That's what a fuse does. Are you with me? So this is how you should say a fuse is a safety device that actually helps to prevent most of your appliance from getting burnt. So that is that about it. So I think that's everything we have to know about all of these things. So let's solve some questions. I have the past question here, but what I will do, I will make a second video to explain some questions on this. Okay, let me just do it under this video. Very. I have about 15 questions here that we are going to look at. So I have some theoretical questions that we are going to look at. This is a past question that contains BAEC, UTME, and post-UTME past question. So let's pay attention. Number one, say Ohm's law states that the ratio V over I is constant for the ratio V over I is constant for what? We say anything that obeys Ohm's law is ohmic. Anything that does not obey. So metals generally obeys Ohm's law. So from this option, they say I steel, I an electrolyte, I silver, IV a diode. Which of the above are correct? A, I and II. B, I and III. C, I and IV. D, all of the above. You know that the correct answer will be what? I and I are steel and silver. They are metals that can come. So they obey Ohm's law. Number 2, a quantity of electricity is measured in what? I asked some students this question and they failed it. A quantity of electricity is measured in the unit of what? A, ampere. B, volt. C, coulomb. D, electromotive. Many of them picked ampere. Is wrong. They say quantity of electricity, quantity of charge. Quantity, that's charge. That's the charge. The answer is coulomb. Let's not forget that, not ampere. Quantity of electricity. Very, very important. Then number 3, the energy needed to move a unit positive charge around a complete circuit is called what? Many will fail this too. A, electromotive force. B, electric potential difference. C, electrical energy. D, kinetic energy. The answer is electromotive force all through the whole circuit. Let's look at some calculations anyway. Now look at this one. They said a current of 180 milliampere. 180 milliampere. Now milli is a subunit that is used. Milli. A current of 180 milliampere, which means 10 raised per minus 3. A current of 180 milliampere flows through a conductor for 5 minutes. The quantity of electricity is what? The current of 180 milliampere flows through this for T equals 5 minutes. What is the quantity of electricity? Quantity means charge, Q. So from our formula, what do we say? We say Q is equal to I times T. 5 minutes. You have to change your minutes to second. This milliampere means 180 times 10 raised by minus 3. The milli here means 10 raised by minus 3. Change 5 minutes to a second will be 5 times 60 because 1 minute equals 60 seconds. So this will be 5 times 60. Then put everything together, we have 180 times 10 raised by minus 3 times 5 is 60. Press your calculator, you will get your answer. So my calculator here, what I have as my answer, 180 times 5 times 60 times 10 raised to power minus 3. 54. The answer is 54 coulomb. And that's option A. So another question we have here is 60 millicoulomb of electricity passes through a conductor for 2 minutes. The current through it is what? Easy to. So 60 millicoulomb. I is here 60 millicoulomb. Time here is 2 minutes. Sorry, millicoulomb is for charge. Charge here is 60 millicoulomb. Let me just solve it. Q is 60 millicoulomb. Time is 2 minutes. And they want me to find current. So we know current is what? I is equal to Q over T. So as easy as this. So all you have to do, put your value, change your millicoulomb to, milli means 10 raised by minus 3. Many people will not do that. And that's why people will just go ahead and solve. They will just remove the milli. It's wrong. Put your milli there. It's a subunit. So milli means 10 raised by minus 3. So 60 times 10 raised by minus 3 over. Change your minutes to second. Anytime they give you time, except the question insists that it must be in minutes. Change the minute to second. And that's it. Then another question that I have here. Okay, let's look at this one. It's a circuit. Now we're getting to the resistance aspects. So they draw a circuit like this. This is how it is. Okay, so something like this. This is the battery. And they drew another one here like this. This is 27, this is 9, and this is 12. So this is a circuit here, and they asked the question. The question was, in the circuit shown, the current delivered by the battery is what? What is the current delivered by this battery? So when they ask you the current delivered by the battery, what do you think? It means the current flowing through the circuit, because the battery is the one that produces the current. Now, one thing I want to take note of, see, take note, they put I1, they put I2, which means a particular, once the current came here, it entered there, it entered there. So it means that this particular one here is in parallel with this one here. Is that not it? Then this one and this one are in series. Are you getting that? So this and this are in series because the current that will enter this one is the same as the one that will enter. So 27 and 9 are in series. But the question is asking me what is the current flowing through the circuit. There are two kind of questions that can come. The two kind of questions are, did they put voltage here? Okay, they say 18 volts. The voltage of the circuit is 18 volts. There are two ways in which this question can be solved. Actually, two different ways. Now, the question indeed actually put I1 and I2 here to show you that there are two ways it can be solved. Firstly, you can either find I1 first, then find I2 next, then add the two together, or you can find it direct. So I'm going to use the two ways for you. So if I'm to find I1, so I'm going to be considering just this place. I'm to find I. Remember this first. If I call this on circuit 1 and call this on circuit 2, circuit 1 and circuit 2 are in parallel. So since they are in parallel, voltage is the same for the two of them. I've told you once, if something is parallel, once it is in parallel with the voltage, it has the same voltage. I explained that before. So the voltage for this circuit is 18. The voltage for this circuit is 18 also. So using Ohm's law, we say V is equal to IR. But the I in this circuit 1 is I1. So I'll call it I1 rather. I'll not just say I because we have two I there. So I1. So my I1 will be V over R by just substituting. What is my voltage? 18. What is my resistance? We only have one resistance, and that's 12. 18 over 12 will give us what? I think that's 0.5. 18 divided by 12. That's 1.5. Sorry, that's 1.5 amp. Is this the current going through the circuit? No, I have to get for this one too. So to get, I'll now move to circuit 2. In circuit 2, we have two resistors, 27 and 9. So are they in series or they are in parallel? They are in series, 27 and 2. The same current flows through them. So for circuit 2, my V remains 18 because it is in parallel to it. My V remains 18. But my resistance will not be 27. My resistance will not be 9. I'll have to find total resistance because there are two resistances there. So my total resistance, how do we find resistance in series? We add them together, right? We just add them together. That will be, ours will be 27 plus 9. That's 36. Are you following me now? So I've gotten my V, I've got my R total. Now I want to find my I2. Using Ohm's law, V is equal to IR. I will not just call it I, I will call it I2. So my I2 will be V over R. You should know this by now. What is V? 18. What is R? 36. 18 over 36, that's 0.5 ampere. So I2 is 0.5, I1 is 1.5. Now the total current flowing through it is the one that comes from the add two of them together. Total current, I'll say IT, I total equals I1 plus I2. 1.5 plus 0.5 has 2 ampere. I've gotten the total current. This is how some students will solve it. We don't do for I1. They will not even know what to do. This is actually what you do. That's number one. Number two, where you can solve it. How to work this off. Number two, where you can solve this is very, very easy. You can solve it together. So I have these two resistors are in series. I want to find my total resistance. I have resistor R1 here, I have R2 here, and I have R3 here. Is that not it? R1 and R2 are in series. So total resistance between these two is what? RT is equal to R1 plus R2. That's 27 plus 9. That's 36. So total resistance is 36. But then this 36 I got here is in parallel to this one. So we find another total. This R2 is not the total resistance in the circuit. We have 3 resistors. I only did total resistance for this one. So that's 36 here. Now the total resistance in the circuit, I also call that one RT. Right? That will be 1 over this one plus 1 over this 12 here. Are you with me? This third resistance, RT, that third resistance, then RT. Okay? Are you following me now? So RT total now, what's this one here? We get 36, 1 over 36 plus 1 over 12. So if I find LCM, I'm going to be having LCM 36. 36 in 36, 1. 1 times 1, 1. If you don't know how to solve LCM, now do your mathematics. 12 in 36, 3. 3 times 1, 3. So we have 4 over 36. 4 here, 1. 4 in 36, we have 1 over 9. So bringing this whole thing back up, we're having something like this. We're having, sorry, this should be 1 over R2. 1 over R2. That's 1 over R2 equals 1 over R2 equals 1 over R1 plus 1 over R2. So that's it. So So our we're adding 1 over RT is equal to 1 over 9. If we cross multiply, you find out that RT is 9. Is that not when the RT is 9? So the total resistance on all of these is 9. Now I want to find the current flowing in the circuit. So I'll simply say using Ohm's law, V is equal to I R. So I is equal to V over R. What's my V? 18. What's my total resistance? That's 9. 18 over 9 is what? 2. Do you not get the same answer as the other one? You can solve it using this. So make sure if you are watching this video, TikTok might not get all the video. Check it. And yes, if you are a JAM student, YX student, or post-semi student, and you need online coaching, you need them to teach you online, make sure you send a message to us. My WhatsApp number is on my bio. Check my TikTok bio or my YouTube. Or simply just use it here. Just call 07036 59 57. So we are going to solve more questions later.